Welcome to the guest lecture on programming with weak synchronization models. So what we're going to do in this lecture is we're going to show you how to do real distributed programs, large-scale, robust, with extremely weak synchronization. So this kind of model will work even on very flaky networks where you cannot give so many guarantees. So the motivation is we want to make it as easy to program as strong consistency and as efficient to execute as weak consistency models. And we will show you a very interesting sweet spot in this space called strong eventual consistency. So the lesson is divided into 3 parts. So the first part, we're going to show you the basic data structures, convergent data structures, which actually give you replicated implementation needing very weak synchronization. And the data structures we're going to show are called conflict-free replicated data types, CRDTs. And then we'll show 2 directions where we actually use CRDTs to build real distributed systems. One is Lasp, is a programming language and its platform where you can program large applications based on combining CRDTs. And second is Antidote, which is a causal transactional database based on CRDTs. So this lesson is brought to you by 3 guest lecturers. So myself, Peter Van Rooij from University Catholique Louvain, my colleague Christopher Meiklejohn, also from UCL, and my colleague Annette Bieniusa from the Technische Universität Kaiserslautern. So this research is done mainly in 2 European projects, one called SyncFree, which is a 7th framework project that recently completed, and the second one called LightCone, which is a Horizon 2020 project that's just started in 2017. So one of the holy grails of distributed systems is to make them both easy to program and efficient to execute. This is the thing we're going to attack. Now, it's clear that strong consistency models like linearizability are very easy to program. Linearizability is like programming sequential system, but it's inefficient. It requires complex algorithms, which you know very well, such as Paxos and multi-Paxos. The other way to do it, the other extreme, is eventual consistency, where you can have many operations concurrently in the system, and they each will eventually complete. This is much more efficient, but it's hard to program because the operations don't know about each other, and each one doesn't know in which degree of completion are the other ones. So the question is, can we get the best of both worlds? So can we combine the ease of strong consistency with the efficiency of eventual consistency? And this leads to an approach which we've called synchronization-free programming. So how can it work? So to explain it, let me first get back to basics. So a distributed system is a collection of network computing nodes that behaves like one system. So what this means is that there is a consistency model that gives the properties of all the nodes working together. So to make this work, the nodes have to coordinate. They have to send each other messages and run some overall algorithm obeying some well-defined rules, and this is called the synchronization algorithm. So for example, reliable broadcast, which we saw in this course, guarantees an all or none property. All correct nodes will deliver the message, or none will deliver the message. So in the synchronization is the reliable broadcast algorithm, and the consistency model in this case is the all or none property. So how far can we go in this approach? The consistency model has to be as strong as possible, and the synchronization algorithm as weak as possible. So we have a tension between 2 opposing forces. So what about an extreme case? So it's good to look at extreme cases when we analyze something like this. So the weakest possible synchronization is no synchronization at all. No rules showing how the nodes should coordinate between each other. So there's no consistency enforced. The nodes basically do whatever they want. Now, this is actually extremely hard to program. You have no help at all from the system. So it's clear that we do need some synchronization. How little can we get away with? So a sweet spot is called strong eventual consistency. So this property states that if one has n replicas and they receive the same updates in any order, it doesn't have to be the same order for each replica, then they will have equivalent state. So it's not after each update, but after n updates, same updates received the equivalent state. And the only synchronization we assume is eventual replica-to-replica communication. That means occasionally the replicas succeed in sending messages to each other, which is a very weak synchronization model. So despite the weakness of this model, very weak, it's actually surprisingly powerful. We can define a programming model that resembles functional programming, concurrent data flow form of functional programming. We can handle non-determinism and non-monotonicity, so it's more powerful than basic functional programming. We can give it an efficient, resilient, distributed implementation. So this is the sweet spot we're going to investigate in this lesson. So in the rest of the lesson, we're going to exploit strong eventual consistency. First of all, we're going to explain how to build these convergent data structures that satisfy this condition. Then we're going to show how to program by combining them. Then we're going to show how to build an actual large database that can do causally consistent transactions on CRDTs. And throughout all this, we're going to give you many applications of this. Let's first talk about convergent data structures. We will define distributed data structures that obey the strong eventual consistency property. And one approach that's been very successful is called conflict-free replicated data types. And that's what we're going to do. CRDTs already are being used by many companies, and here's a bunch of logos of companies that are already using CRDTs today. So let's first define formally what is a CRDT. And what we're going to define is what's called a state-based CRDT. So it's defined as a triple. So the first part of the triple is the configuration, basically the state on each of the replicas. There are n replicas, and each replica has a state Si. And the particular property is that Si is an element of big S, which is a join semilattice, which I'll explain in a moment. There's also a query function. This is basically a read, an external read, and a mutator, which is basically an update operation. And the particular property of the updater is that it will inflate the value. What that means is the lattice is kind of like a ladder going up, and the mutator will only go up on the ladder. So M of S is always going to be higher than S. It's basically going to be higher on the semilattice than the original state. And the other operation of the state-based CRDT is that the replicas will periodically send state to each other, and each of the replica will basically merge its own state with the state of another replica. So that's how the CRDT is defined. Let me explain very briefly what is a join semilattice, and then I'll show you an example of how it all works. So you'll see that despite the apparent complexity of all these symbols on the slide, it's actually a very simple idea. So a join semilattice is first of all a partially ordered set, and the second point is it has a least upper bound operation. That means you can take any two elements of the partial order, and you can merge them together, which is called the join, and this will go up in the partial order. So the nice thing about CRDTs, why are we defining them like this, is that they automatically obey strong eventual consistency. So assuming eventual delivery, what that means is that an update delivered at some correct replica will eventually be delivered to all correct replicas because of the synchronization. So this is the eventual replica-to-replica communication that guarantees this. So an object is strong, eventually consistent if all correct replicas that have delivered the same updates have equivalent state. So they don't have to do any kind of coordination. They will automatically get equivalent state. And there's a theorem where you can prove a state-based CRDT, the way I have just defined it, will automatically satisfy strong eventual consistency. You can prove this by induction on the causal histories of the deliveries. This, if you want to see the proof, I'm not going to give it here. It's given in the INRIA research report that is referenced in the bibliography. Okay, now enough symbols. Let's now look at an actual CRDT, and we'll look at a very simple one, which is called a grow-only counter. Each replica stores a vector, so here, and the C's are the values of the count. So the CI's are natural numbers, and each replica can do an increment, and the operation is very simple. What it does is it basically increments the I value of the vector. And you can also read the value of the count, which is basically the sum of all the elements of the vector. And the join operation basically takes the max pairwise of all the elements of the vector. So the idea is that the state vector will store what you know about the increments done at all replicas, and eventually all the replica vectors will converge to know all these increments. So now let's do an example. So here's a CRDT with 3 replicas, R1, R2, R3. Initially, the values are 0, 0, 0. And now let's do some operations. So let's do an increment operation here on replica 3. This causes the state to go to 0, 0, 1. Now let's do an increment operation on replica 1. This causes its state to go to 1, 0, 0. So we have 1, 0, 0, 0, 0, 0, and 0, 0, 1. Now, there's also join operations happening. These kind of happen automatically. These are the synchronization, the replica to replica communication. So occasionally, the replicas will talk to each other. So here, the replica will basically, R3 will send its state to R2 through this join message, and the state will then be merged. So the 0, 0, 0 and 0, 0, 1 will be merged together. And this causes it to become 0, 0, 1, the pairwise maximum. Now another join operation now comes from replica 1. This joins 1, 0, 0 and 0, 0, 1, and that becomes 1, 0, 1, the pairwise max. Now let's go on and do some more computation. Let's do another increment at R1. So its state becomes 2, 0, 0. And now let's say there's a join going to R3, and this causes the R3 state to become 2, 0, 1. Which is the max of 0, 0, 1 and 2, 0, 0. Now the pairwise max of all the elements of the vector. Now we go on, and eventually the joins are going to be going more and more. So there's going to be a join from R2 to R1. This causes R1 to become 2, 0, 1. And eventually a join will happen from R3 to R2. This will cause it to become 2, 0, 1. And what happens is, if you look carefully, all the replicas have now converged. They all have the same state, 2, 0, 1. And 2, 0, 1 basically corresponds to an increment count of 3. 2 plus 0 plus 1. So all 3 replicas have the same state, and we didn't have to do any more synchronization than just replica to replica communication. Okay, so that's basically how CRDTs work. But the grow-only counter is a very simple CRDT. Each replica is only storing a single vector, and you can see the operation is pretty simple. And it actually behaves sort of like a vector clock, if you remember vector clocks. Now the big question is, can we do more than this with CRDTs? Can we, for example, both increment and decrement? Or can we do more complicated data structures, for example, sets, where we can add and remove elements? And the answer to these questions is yes, we can do all that and more. And in the next video, we'll show you some more sophisticated CRDTs. Let's now look at some more powerful CRDTs. In the previous video, we looked at the grow-only counter, was a very simple one. We're now going to show the up-down counter, so a counter that can both increment and decrement, and the observed remove set, which is a set where you can add and remove elements. And this is only the tip of the iceberg. There are many even more powerful CRDTs, which some of them actually have quite complicated algorithms for doing the mutate and doing the join operation. And in the bibliography, you can find out more about them, and you can see how far it can go. We're also going to compare CRDTs with replicated state machines as a way to implement distributed data structures. So what are the differences between the two? So let's talk now about the up-down counter. So first I'll give it a formal definition, which is similar to the formal definition of the grow-only counter, except that now we have a bigger vector. We have in each replica the increments, so the up values, and we also have the decrements, the down values. And both of these are natural numbers, so non-negative. And each replica will now accept an increment or a decrement. The increment will update the UI, and the decrement will update the DI. And then the value, val I, is basically the sum of the U values minus the sum of the D values. And the join operation is basically the same as before. It's the pairwise maximum of the vectors. So how does it work? Both the increment and decrement inflate the value. So we're always moving up on the lattice. The val then calculates the correct value by doing a subtraction. And as before, exactly in the same way as for the grow-only counter, all replicas will converge to the correct value using only replica-to-replica communication. So this is how you can represent values that don't always grow using a lattice where the values do always grow. Let me now explain the idea of the set where you can add and remove. So this is a set that's known in the Crdt community as an OR set, or an observed remove set. It supports both adding and removing, and the outcome corresponds to the sequential specification of the set if you do sequential operations. In case of concurrent add and remove, the add will have precedence because it's actually more general than a sequential set. It's a concurrent set, so you have to also specify what happens in the concurrent case. So this is how we define it. So the intuition of this, to make it work, is that we will tag each added element. We will put a unique constant value to correspond to each add operation that we do. When you query the value of the set, you will not see this tag. It's internal to the Crdt. It's what we call metadata. And when you remove an element, we use the tags. We basically remove the tags in a clever way. So here's an example of an execution. So as before, we have 3 replicas here, and we will do operations. So we first do an add one operation. Now it's a little bit more complicated than the grow and the up-down counter, because we will create, for the adding of the 1, we will create a triple which contains the 1, a unique value which corresponds to the add, and the third value which corresponds to the removes. It's an empty set because we haven't done any removes yet. Now assume we do remove 1 later. What we'll do is basically the second value of this set will tell me if I've removed the element. So we basically move the B also to there. We also have join operations as before, which do merges. The merges basically do the pairwise union of the values of these two sets. Now assume replica 1 also doesn't add. Here we have also a triple, 1A, empty. The A is another unique value. So each add of 1 will have a different unique value. Now the joins happen. So here's another join happening. The 1BB is joined with 1A empty. This gives me 1ABB. So basically, I have added 1, removed 1 on this path, and on the other path, I have just added 1. So what that means is that the 1 is actually still there, because this first replica that didn't add, this particular add has not been removed. See, the removes work for particular adds. In order to remove an add, the add has to be in the causal history of the remove. So after a few more joins then each of the 3 replicas will have again the same value, which is 1ABB, and this corresponds to 1 being in the set, because the adds are strictly bigger than the removes. So each replica stores a triple, EAR. E is the element, A is a set of adds, R is a set of removes. If A minus R is non-empty, then E is in the set. And finally, very importantly, all adds all updates, both adds and removes, will cause monotonic increases in EAR. The A and the R will only increase. So it's still going up the lattice, even though we can add and remove, and even though with only replica-to-replica communication, all three replicas will agree on the value at the end. So now you see a little bit more of the kind of things you can do with CRDTs. Many more CRDTs have been invented. So here's a short list of them. Different kinds of registers, different kinds of sets, maps, which are sort of like dictionaries, pairs, which are basically a pairing operation that you can use to build more complicated composed CRDTs, including recursive versions where the maps contain maps and so on. Counters, you've seen the unlimited counter, also restricted counters or bounded counters, which will not allow the value to go beyond a certain limit. Also, for example, graphs, directed monotonic DAGs, graphs with editing operations on them, where you can add or remove, edit the graphs in different ways. Also different kinds of sequences and lists, and more complicated CRDTs used for collaborative editing, for example. Now, to step back a minute, we have now seen two ways in this course to define distributed data structure. We've seen the replicated state machines, RSM, and the CRDT. So what's the difference between the two? Well, basically, the RSM approach ensures that the replicas are equal to each other after each single update. So there's a consistency after each update, and the consistency is guaranteed through a consensus algorithm which is run after each update. Whereas the CRDT approach ensures consistency when the replicas have received the same set of updates. So it's not guaranteed after each update, but it is guaranteed for replicas that have seen the same updates, and that needs only node-to-node communication. And in many cases, this is good enough. It's a form of convergent consistency, and it is different from RSM, but requires much less synchronization. So, another point on CRDTs, what's the catch? If CRDTs are so great, why aren't more companies using them? Well, in fact, many companies are using them, even they don't tell you that they're using them. It's part of their secret sauce. They're not necessarily going to tell you, and their number is growing. But still, why isn't everybody using them? Well, actually, there are some trade-offs in using CRDTs. First of all, they require metadata, as you've seen with the OR set. In order to guarantee monotonicity, causality, you have to add extra information. This information has to be stored, it has to be sent. So that's some overhead. Second of all, if you add and remove, the state is always growing, even if you remove. So you use techniques like tombstones, and this causes an accumulation of data that you have to remove occasionally in order for it not to gather too much. This requires some form of garbage collection that can be non-synchronized. Finally, some particular CDTs, like last writer wins, they have some clock skew effect, but that's because it's using the word last. So the most important catches are the metadata and the need for eventually some form of garbage collection. Now, in the rest of the lesson, the rest of the videos, my colleagues Chris and Annette are now going to explain two important directions of this work. So first of all, Lasp, which is a programming language and a platform that is based on strong eventual consistency, letting you build applications, and Antidote, which is a causally consistent transactional database, a large-scale database, also based on strong eventual consistency. And with both of these together, you can build large internet applications using CRDTs.
My name is Christopher Meiklejohn, and I'm going to continue our lectures on programming weak synchronization models. So for this talk, I'm going to review conflict-free replicated data types. I'm going to look at one special case of a conflict-free replicated data type, the observe-remove set, and then I'm going to talk about problems of composition. So to review, what are CRDTs? CRDTs are abstract data types that can look like sets, counters, registers, flags, or maps. That satisfy the property of strong eventual consistency on a per object basis. What this means is that under concurrent additions, with minimal coordination, I always have a way to take any two objects and deterministically merge them, allowing each replica to converge just by observing all of the messages in the system. And CRDTs are formalized using what's referred to as bounded join semilattices, which mathematically means that for any two possible states the object can take on, there's always a way to join them and combine them, so merge them together. Now, one special case of a CRDT is what's referred to as the observe-remove set, which allows us to add and remove elements with minimal coordination and guarantee get the same outcome under concurrent additions. It's worth noting that this set under concurrent additions and removals, which normally don't commute in a sequential system, they will resolve to the concurrent addition winning. So in this example, I'm going to have three copies of the data here represented by replica A, B, and C. And I'm going to model the state of each replica as a triple, which will be the value in the set, a set of unique additions, and a set of unique removal tokens. And we can see that here. And so what this basically says is when I added the value 1 to the set, I generated a unique token here, alpha, represented by this A, and I put it into the add set. So 1, this set of A, the singleton set of A, and the empty set of remove says that 1 exists in the set because it was added at logical time A with no removals. Now concurrently here, if I add 1 to the set at replica C, before it's observed the addition from A, it will generate a different token, here represented by beta, which shows that it was added to the set at logical time beta and not removed. Now to model removes in a monotonic way, in a way that always merges, I take the additions and I union them with the removals. And so here it shows that I saw 1 added at logical time B, and then I also saw it removed at logical time B. And so at this point of the execution, the set has no values in it. And so these here are the replica-to-replica messages where the values are propagating between replicas. Now at the end of the execution, the way I achieve convergence is that as each replica receives messages from the other replicas, it just takes a pairwise union of the adds and the removes for every value in the set. And we see that here at the end of the execution, 1 is still in the set, because while it was added at time B and removed at time B, it was added at time A and nobody removed it at logical time A. So in this example, 1 remains in the set because the concurrent addition and the concurrent removal, the concurrent addition from node A, 1. So let's talk about problems of composition. So in terms of composition, we're going to consider observe-remove set. We're going to drastically simplify it here by only keeping 2 replicas in play. And I'm going to have it so 1 remains in the set. It's basically going to be the same situation as before. 1 will remain in the set. I'll have an addition or removal and a concurrent addition that will win. Now, if I wanted to program with the CRDT, for instance, if I wanted to take the value of the CRDT, the set with 1 in it, and apply a function to that set, such as doubling the elements in it to make this as simple, the way I could trivially build this is a process that reads the set as it changes each time, and then applies the update here. So we see that the set was 1, it went to 2, the set was empty, it went to nothing, and then it was 1, and it went to 2. Now, in a distributed system, to achieve fault tolerance, in the same way I replicate the data, I would replicate the entire computation. So I would have the computation running here and the computation running here. Now, if for some reason, and now as we've seen with CRDTs, if messages get delivered out of order, it doesn't change the result. They still will always achieve the correct convergence. However, if I, in this case, trivially take the values and I don't take this metadata and map it through the function, the problem I can run into is that a delayed message can change the outcome of the execution. It doesn't necessarily merge. I have no way of merging the outcomes of the computed value in the same way I have that I can operate on the source values because I don't have the metadata. And so while some parts of the computation, such as this section highlighted here in yellow, while some parts of the computation will converge correctly, any message that's delayed that doesn't carry that metadata will not compute the correct result. And so what we've seen is that while the observer moveset in isolation allows us to model additions and removals without coordination, as soon as we go to read that value and do anything with it, we break out of the safety because we no longer carry around this internal metadata, which is the important part of ensuring convergence. And so this is what we refer to as the composition problem. And this is what we'll be discussing in our next lecture. My name is Christopher Meiklejohn, and we're going to continue our lecture on programming weak synchronization models. And so in the previous lecture, what we talked about was the observer moveset, one particular instance of a CRDT, and the problems of composition. So how we can read the value and perform some computation on it without breaking out of this safe world in the metadata where we sacrifice convergence. And so what we're going to talk about today is how we begin to address the problem of making sure that computations with CRDTs are convergent. And so the system we're going to talk about today is called Lattice Processing, or Lasp for short. And what the Lasp system is a way to express asynchronous data flow computations over streams. And so in our system, all of the streams that we have are CRDTs. In our system, the only data abstraction you have is the CRDT. And each CRDT can be seen as a stream of states that's monotonically growing. And so the programming system allows you to read some state as it's evolving and produce some output based on that input state. And it does this in a way where confluence is preserved. So the composition is guaranteed to be mergeable and preserve the all the properties of strong eventual consistency. So let's talk a little bit more about what I mean when I say confluence. And so as a programmer who writes distributed applications, I want to write a computation where I think about just one input value, and a computation I write over that input value should produce some output, and ideally, regardless of how the system is distributed, that should be guaranteed. It should be deterministic. And so even though we write our applications this way, when our applications are distributed because we want fault tolerance and high availability and low latency, what we really have is multiple copies of our inputs, multiple copies of our computations, and multiple copies of our outputs. And so in this example, I have a distributed system made up of 3 nodes. I have 3 copies of the input, 3 copies of the computation, and 3 copies of the output. Now, one possible way an event could be delivered in the system, if we're not synchronizing and using minimal coordination, is that events may arrive at a given node A. The A's might propagate their values to the other A's. Each of those A's runs the computation, produces some output B. Now, another possible way these messages might be delivered is that an input may arrive at A, I may produce the value B, and then B's will propagate their values to the other B's. So this is another possible way messages can be delivered in the system. And so there's a number of possible ways these messages can be delivered, and that only grows as we increase the computation here and increase the number of nodes. And so from the programmer point of view, what we'd like to see is that all of these possible delivery schedules, what the system guarantees, is that all of these possible delivery schedules produce the same result as this single specification, the sequential specification. And so what the system tries to do is generalize what computations are able to be run here safely, so that property holds. That's what our system guarantees. So we'll look at a little pseudocode example of what the system looks like. And here we create an initial set called S1. In S1, we'll add elements to the set. So here we're adding elements 1, 2, and 3. Here we create a second set. And then what this expression here says is that I want to take the input values S1, and I want to produce some output S2, and I want that output to basically be this function applied to every element in the set. And so this doubles every element in the set. And so what we've seen in this section is how to look at computations in a way where the output of computations are are guaranteed to be deterministic with arbitrary distribution, and we've given a brief overview of what the Lasp system does, what it provides. So I'm Christopher Meiklejohn, and we're going to continue our lectures on programming weak synchronization models. And so in the last section, we talked about the problem of composition and gave an overview of the lattice processing system. And so now we're going to, in the next series of lectures, talk more in depth about how the system achieves the goals that we outlined in the previous. And so the way the lattice processing system works, again, as we talked about in the last section, is over streams of input values that are monotonic, which means that every state in the stream will be greater than or equal to the previous state. And so each CRDT can be seen to evolve by either growing or staying the same in a stream. And so the way the system works is that if I want to express some computation based on some input, produce some output, I have a process that is reading the input state as it grows and producing some output state that is either staying equal to its previous state or growing. And so we take input streams and produce output streams. We have processes that facilitate this. And because we're running in a distributed system where nodes can fail and messages can be delivered out of order, sometimes we may see some state that comes from the past, which is less than the previous state. And to ensure that the computation remains correct, we only read values that grow over time. And we'll see how we enforce this, what's referred to as an inflationary read. So let's look at what a stream looks like. And so in this example, I have two clients that are executing. We're going to use the OR set representation we used in the previous sections. So this, again, for each element in the set is a triple of value, addition token, and removal token. And as each client executes, it will cause its local copy of the state to inflate, and then that copy of the state will be merged with a replica, and then the replicas will communicate once another. So we can think of the clients as threads on a machine or processes on a machine computing with the local replica. So in this example here, client 1 adds 1 to the set, generates unique token A, as we saw in the first lecture on Lasp, and the removals are empty. So it says 1 is in the set because it was added at logical time A and never removed. This set is propagated to replica A. Now when client 2 executes, it generates its own token for adding 1 to the set, this token beta. It's not removed, so 1 is in the set because it was added at logical time beta and not removed. And then it propagates its state to the replica, and that state is merged in. So we see here that we have 1, we have A, B, no removals. So C1 then issues a removal, takes the add tokens, unions them with the removals, propagates its state to replica A, which is then merged in, and this continues. So we see that clients operate with their local view of state. They can ask for state from the replica if they want a more recent view, but they can execute without having it. So they can execute with a partial state. And we see that replica A always is growing. It's always monotonic. So this is a stream. So replica A is one stream in the system. And the stream is monotonic. It's always growing. Even the clients are monotonic. So the clients have partial state. It's monotonic. Replica A is monotonic with the full state. Now, the way the processes in the system work is that the processes read that monotonic stream of states. So here, again, we have replica A. This will be the same replica A we saw in the last slide. This state will be growing, and the process will say, I would like to read state from you, and it needs to be greater than the last state I read. Here, that state is the bottom, the empty set, because it hasn't gotten any state yet. And so when replica A gets a value where 1 has been added at logical time A, it sends a notification to process 1 to say, yes, the state has changed. It's been an inflation. Process 1 applies the function to that state to produce an output. So again, every time a replica changes, the process will compute a new result. And we see here that, again, our operation is map where we double the elements. And in this example, it's pretty trivial. All we have to do is modify the element, map the metadata through. So again, this will continue. We'll say I want to read a state that's greater than the last state I read. When the state changes, it gets a notification, it applies the function and produces a new output, again mapping the metadata through, modifying the element. And so this continues. And what's really nice about this system is that given all of these states are monotonic, I can omit entire interleavings, such as, for instance, when messages are dropped on the network, without sacrificing correctness of the application, as long as I deliver some final message at the end of the execution. So I can omit an arbitrary amount of messages as long as I deliver some final message, and that will guarantee the result is correct. And so what we've seen here is that the power of monotonicity in applications with processes is that we can arbitrarily drop a series of messages, not have to worry about things because the subsequent message will subsume all previous messages. And we've also seen that it allows us to have idempotence so that we can replay earlier messages. So this gives us this allows us to be safe when it comes to message drops and message replays. My name is Christopher Meiklejohn, and I will be continuing the lectures on programming weak synchronization models. So in the last section, we talked about the Lattice Processing System, or Lasp for short. And we examined how Lasp reads streams of monotonic inputs, applies functions to them to produce streams of monotonic outputs. Now, in performing those computations, Lasp can't look at just the values alone. It must also consider the metadata to ensure convergence. And so in this lecture, what we're going to look at is how Lasp knows how to perform the appropriate transformations on the metadata representations. Specifically, we look at Lasp operations on the observed remove set, which we talked about in previous lectures. So we'll start by looking at the map. So the map is similar to a map operation in functional programming, where a function is applied to every element of a set to produce a corresponding element in the output set. So in this example here, we have two lines. The first one, and so this will be the same for all of the examples we'll look at. The first one will be replica C. So this will be just one of the replicas. And then the second line will represent the functions, the map function applied to the values in replica C. So when 1 is added at replica C here, it generates again the unique token B to say that 1 was added at logical time B and not removed. And then we have a process that's reading those inputs, computing those outputs. So the transformation for the map is fairly straightforward. What the map function will do will apply the function to the value. Remember, our representation for the observe remove set is value, add tokens, remove tokens. It will apply the transformation to the value, and then it will map the metadata through accordingly. Now when B is removed, even though the set no longer has elements in it, as we see it's empty, the metadata is not empty. The metadata is monotonically growing. The map operation is executed, and it's run on this internal representation, not the external representation. And then this will produce a corresponding element in the output, which is 2, removed at B, removed at B. So we still perform that transformation on the values, and then map the metadata through accordingly. Finally, this continues as the execution evolves. So for the filter, the way the filter operation works is it takes a predicate. If that predicate is matched, it allows the element through. So again, we look at the same kind of setup. We have a replica, and we have the function applied to the values of the replica. This is our input stream. Again, this is our output stream. And so in this first example, we're going to allow elements through which are odd. And so the one kind of just gets passed through transparently. We map that metadata through. And then this continues through the execution. Now, regardless if the set has values in it or not, the predicate is still applied and maps through. Any elements that don't match the filter are omitted completely. So we see here, even though 1 is removed, the set is empty, we still map the metadata through and preserve the transformation through. Now the fold is a way to take a set and aggregate the values into the set to produce some other type of data structure. So another type of CRDT. For instance, we could count the elements in the set to produce a counter. And so we can think of the fold as basically being a morphism between two types of CRDTs. So I have some CRDT A, so I have a collection of A's. And then I want to produce some B based on that. So this could be a set of A's, maybe integers, and then I want to produce some counter B, which is the number of elements in the set, for instance. Now, the fold has to be restricted in expressiveness because traditional folds in functional programming operate over lists. Lists have order. In CRDTs, we don't have a list data type. There are some sequence types that are used for collaborative editing, but we don't actually have a list. And so this implies that since we're operating over a set, elements can appear in any order. The function that's used to combine the elements must be associative, commutative, and idempotent, which means that we can tolerate different batchings of orders, different orders of elements, and we can apply the same element multiple times. And finally, since we have to deal with unique add tokens and unique remove tokens, we must have an inverse for every operation we perform. So for every operation, for every add token, we apply some function. And then for every remove token, we apply the inverse of that function. So here's an example that's slightly complicated where we will take a set and we'll produce a CRDT counter. And that counter will be counting the elements in the set. And so in this example here, we start, our combining function will be cardinality to compute the cardinality of the set. And what we do is we take this metadata representation here and we produce a compatible metadata representation for the target type. And so this structure here is the structure of a positive negative counter, which is the combination of two grow-only counters. So as the process continues, we see that the add tokens are mapped into the increments and the removal tokens are mapped into the decrements. Similarly, that process continues, so we have two increments and one decrement, leaving us with 1. At the end of the execution, we see that the cardinality is correctly computed to correspond to the contents of the set. Now we'll briefly talk through the set theoretical operations, union, product, and intersection. And so in these examples, we have an A and a B. We have a left side and a right side of the operation. So in this diagram, we'll see that this is our left side of the union, and this is our right side. And so these two streams are being combined into one. And so what we do is every time the source changes of the left side and the source of the right side changes, the union will compute a joined metadata. And so we see here that the union actually is just the merge function or the join for the observe remove set. And so all we do is combine the elements, basically taking the pairwise union. In terms of the Cartesian product, for the left side and the right side, we don't want to produce any elements until we at least have an element from both sides. So we see that the Cartesian product, when we have just the left, is the empty set. But then as we get more elements, so here we have the 2 coming from B, we produce 1 pair. Similarly, this continues as the execution evolves to produce the final output. Now the intersection is rather straightforward because the intersection is really just the combination of the operations we've already seen. And so again, we have a left-hand side and a right-hand side. And the intersection can be expressed as taking the Cartesian product, filtering where the left side and right side of the pairs are equivalent, and then mapping it to a single element, which is just reducing the pair into a single element to compute the intersection of both A and B. And so what we've seen in this lecture is how the metadata transformations are applied in the Lasp system, how we read streams of monotonic inputs to produce streams of monotonic outputs. And we map that metadata through to ensure that the outputs observe the same properties, specifically strong eventual consistency, as the inputs do. My name is Christopher Meiklejohn, and I'm going to continue the lectures on programming weak synchronization models. So in the last lecture, we talked about the metadata transformations that the Lasp system does. Previously, we talked about Crdts, the composition problem, and how Lasp addresses the composition problem. And now we're going to talk about an actual application that we built with the Lasp system. So we're roughly going to just talk about the structure and the unique properties of the application that make it suitable for developing and exploiting availability and the concurrency in the system as Lasp provides. So the application we're going to talk about today is the Advertisement Counter. The Advertisement Counter is an application scenario that comes from Rovio Entertainment, the creator of Angry Birds. And basically, the design of the Advertisement Counter is to enforce a lower bound invariant. And what we mean by this is that there will be a series of advertisements that are going to be displayed, and they're going to be paid or shown according to being shown a minimum number of times. So this is a lower bound. We have to enforce that it's shown a certain number of times, but we can exceed that number. A unique property of this application is that clients will go offline, which means that clients, because we're focusing on the mobile case, will have limited connectivity, and we need these clients to continue to make progress, continue to make progress in the sense that they show ads, even if the client happens to be disconnected, and so we can't involve anything that talks to the server for every request. And finally, we want to ensure that we don't lose any ads. So we're okay with displaying ads more times than required, but we never want to not count an ad. We always want to know the actual number it's been displayed. So let's talk about what we mean about losing updates. So again, we'll go back to this diagram that I've been using for the lectures, where I have two copies of the same data structure. Now, if I assume that I model the number of times that advertisement has been displayed using a register, that means at the start of this execution here, I'm going to set the value to 1 at replica A, say the ad's been shown once, and then I'm going to send that message to B. So when the message arrives here, A and B will be in agreement that the value is currently 1. Now, if replica A then shows another ad and says the value is now 2, but replica B also shows an ad and says the value is also 2, I can't model this using a natural number because I need to have some way to resolve things. So how do I know that the 2 from A is a different increment from the 2 from B? And so even using a function that allows us to merge things, like at the max operation, for instance, still will not compute the correct result here. And what we've seen is that this composition is incorrect. This is not a compatible lattice for the application. And so what we really need to do is we need to replace this register that we're writing here with something like a PN counter or a G counter, which has been discussed in previous lectures. So let's talk about the design of the application. So we settled we're going to use G counters. And so the general application flow works like this. We have a server. Clients will read state from the server. So they'll read the ads that should be displayed, the current count of the ads, so what the counters are at already. Clients will then locally mutate this state, so they'll increment the counter, saying that the counter is now 4, the counter is now 5, the counter is now 6. And we'll use the Crdt counter to ensure that we can identify concurrency correctly. And clients will push those updates back to the server periodically, merging in, creating that monotonic stream, so we'll see the state is constantly growing. And then the server is going to enforce an invariant over that state. So if the ad has been displayed a minimum number of times, it will mark the ad as disabled. And so we saw in the first lecture on Lasp around the observer move set how we can remove something from a set monotonically in a way where we don't need coordination. So we have a combination of our counter that allows us to keep track of things and merge correctly, and we have our observer move set that allows us to model removals of items from a set in a safe way as well. Now, the client will then periodically synchronize with the server, or propagate state between the client and server to update the list of ads that should be displayed, the list of counters that should be displayed, what the current values of those counters are. And then any client that is unable to communicate with the server may violate the invariant or further violate the invariant. So again, this is a lower bound invariant. And so if a client doesn't talk to the server frequently enough to find out that the ad should no longer be displayed, we could continue to show the ad a number of more times. And this is why it's important to not have an invariant that is strict in both directions. So in the Lasp system, we designed this application. It roughly breaks down into 3 components, which we'll highlight here. So this is kind of the outline of the application. We start with the asynchronous data flow. So the asynchronous data flow basically says that we're going to have a number of ads, and we're going to have some contracts. Contracts say which ads I can display. I'll take the Cartesian product of these, which produces ads cross contracts. Then I'm going to filter out the ones that don't have contracts to give us just ads with contracts. And then I will create a final list of ads to display. Now this can be expressed as the Lasp data flow. And what's nice about this is that this data flow can actually be expressed as SQL, because this is basically just taking an inner join of 2 sets where the values are equivalent. Now once I have the set of ads to be displayed, then what I want to do is basically have a series of counters that are initialized, and I seed the initial list of ads and the initial list of counters. So this is our initialization phase. And then finally, the way the invariants work in the system are that for every single ad that I have, which maps to a counter, I want to enforce some invariant that says as soon as a lower bound condition is met, I want to remove the ad from the set of ads to be displayed. And so we set up our initial condition. This is our monotonic condition that's triggered, which triggers a removal on the observed remove set. This again is our G counter. So what's nice about the design of the advertisement counter is that the flow of the application is completely monotonic. Again, like I said, we can disable advertisements and contracts using observe remove set. So we can do this in a nice monotonic way that requires no coordination whatsoever. We can use convergent data structures and the Lasp system to arbitrarily distribute the application. So all of those boundaries I showed in that diagram are places where the application could actually run on different nodes of the system. So we could run that entire data flow on one node, or we could take every single component of that data flow and run it on a different node. And so the CRDTs make it safe for, the CRDTs combined with Lasp make it safe for arbitrary distribution. And then finally, we can think about how far we violate that invariant as how far we diverge off of that lower bound. So if nodes in the system talk to the server more frequently, we synchronize more frequently, or propagate state more frequently, we'll see less of a violation on that invariant. So if we force a client to propagate state and pause between every single advertisement being shown, we'll have much less of a violation off that invariant than if clients are allowed to only propagate state or synchronize with the server once a day, for instance. Okay, and so what we've basically seen is that the Lasp system is nice because application behavior doesn't change when the system is distributed in arbitrary ways. It basically presents a subset of computations that are safe for transparent distribution, and we see that we actually can build useful applications. Hi, I'm Christopher Meiklejohn, and I will be continuing the lectures on programming weak synchronization models. So what we've talked about so far is the design of the Lasp system, which addresses the composition problem with CRDTs. And we've seen an example application that's been written specifically for the Lasp system, the Advertisement Counter for Rovio Entertainment. Now, what we're going to talk about today is the final component of the system, which is a work-in-progress runtime system that we call Anabranch. So what is Anabranch? Anabranch is addressing the problem that the Lasp is not enough. So CRDTs address the data structure issue. Lasp addresses the composition issue. However, you still need an efficient way to disseminate the data structures on the wire. You need a mechanism for ensuring that the messages are eventually delivered, which is one of the core criteria needed to satisfy strong eventual consistency. And we need a way to do this efficiently and at scale. So Anabranch attempts to address this problem by providing a layered approach to a runtime system designed for distributed applications that are written in Lasp. So Anabranch has 2 core components. It has mechanisms for state dissemination and for management of the cluster topology and membership information. To achieve efficient state dissemination, Anabranch takes advantage of a technique referred to as delta state synchronization, which is done by colleagues of ours in Portugal, that attempts to address the problem of incremental dissemination of state and ensuring that clients all eventually receive all copies of all the messages that were sent, which is referred to as anti-entropy. And then finally, we'll briefly talk about some scalability numbers based on an initial performance evaluation. So what do I mean when I say Anabranch is a layered approach? So Anabranch is broken up into kind of 3 core areas. The first is that it has a database underlying it that's used for persisting and durability of the CRDTs themselves. So we can think of Lasp as a programming model that operates on data structures that are stored in an underlying highly scalable, efficient, fault-tolerant database. Now, the second component of Lasp is its membership component. And so to operate at large scales, specifically if we were going to run the advertisement counter on hundreds of thousands of nodes, we need to have a membership protocol for identifying where the servers are, where the clients are, who the clients are. And arguably, we'd want to run this in varying topologies depending on where we're deploying our application. So some of these applications may be deployed in a client-server topology, where some may be deployed in a peer-to-peer topology. And finally, the most naive approach to addressing the membership and dissemination problem is to just flood the network with messages and have every node know about every other node. However, while that is highly fault tolerant because of the amount of redundancy that's introduced in the system, this can be very inefficient for large clusters. And so Anabranch has a component for optimizing via trees or other optimizations that can operate either together, hybrid mode or not, that allow us to efficiently disseminate state on the wire. And so the design of the system roughly looks like this. So sitting at the topmost layer here is where we write our applications. So this is where our ad counter is. And then we have a language extension that is in our prototype implementation of Lasp and Erlang that provides the metadata mapping facilities and the combinators that you've seen. Now, second component here is the durable backing store. So in topologies where you need durability, maybe you want to treat a single data center as a logical node in Lasp, you could have a distributed hash table, maybe using strong consistency or weak consistency, provide your interface to Lasp's database layer. Or in some cases of the ad counter, you may have mobile phones that don't need fault tolerance or durability. And so this KV abstraction, which is our database, provides an abstraction over the storage of values in the Lasp system. Now, the last component is our dissemination component. And so we have varying topologies. There are multiple peer-to-peer topologies. There's a full connectivity topology. There's a client-server or star topology. Each of these topologies can operate. We can run multiple of these topologies at the same time. Clients can participate in one or many. And then this produces our membership overlay. Once our membership overlay is computed, we have an optional broadcast layer that is then used to further optimize the overlay to get performance gains. So let's briefly talk about how delta state CRDTs work. So as you may have noticed from the previous lectures, sometimes these data structures can grow very, very large. For instance, the G counter grows large on the number of clients that are accessing the G counter and writing to it, where the observe remove set, as we saw in the first lecture, grows on the order of operations. And so these data structures can get very big. And so we need a mechanism for efficiently disseminating these. Now, delta state CRDTs operate locally, so we mutate those objects locally at each replica, and then we buffer differentials and periodically gossip those. Now, a core component of this technique is that since these updates must be periodically gossiped and buffered, and they have to be buffered in causal order, this means that clients need to only know about some subset of nodes in the system, otherwise they have to buffer for too many clients. So for instance, if I ran a 1 million node network, each client, if it was a fully connected network rather than a partially connected network, would have to buffer updates for every other client in the system. And so the core part of making this technique work is that we need to have a topology that is very few members but maintains connectivity. So to give you a rough idea how this works, we'll use this typical diagram that we've been using for most of the lectures, where we have replica C here. And then we'll have 2 buffers for replicas A and replica B. This will be for the updates. And these will be the buffers at replica C. So this is replica C's buffers. Now when the first update is happening here, we add 1 to the set with B. This is our set. We buffer the update there. Now, we can't minimize this change representation because this is already the most minimal representation that we have. And similarly, when we go to perform a removal here, we have to buffer that change that well as well. Now, where we get the benefit is when we add a different element to the set, such as 2 with unique token C, then we can buffer just the update for 2, and we don't have to send this redundant information like we saw that was being transmitted in earlier modes. And so this is a minimal representation of the change to this data structure that was enacted at this moment. So again, these buffers are in per object causality, and we will send these buffers in order, wait for acknowledgements before flushing the buffer. Now, just kind of talk briefly about the scalability. We've been working very hard at evaluating the scalability of Anabranch, and so far we've seen that we can run Lasp applications at 1,000 nodes. We've done this in the Amazon cloud computing environment as well as the Google Container Engine environment, and this is very nice. The prototype is written in Erlang and has very nice scalability, considering that the biggest Erlang cluster that is running in production is around 200 nodes. So we're continuing to work to get this to 2048 and 4096 by the end of the year. Finally, what we've seen is that by building a bunch of small components that interact on nice, well-defined boundaries, we can build a very scalable system. So we have the broadcast component, as we saw, we have the membership component, and finally the programming language component and the backing data store. So each of these is a series of libraries that kind of come together, provide a comprehensive system that scales very well. And so basically, to wrap up, what we've seen is that the Lasp programming system is more than just a programming model. It's taking a strong foundation of CRDTs that provide determinism and conflict resolution, very well designed for the use in distributed systems. It extends it to provide a programming system so that developers can easily write applications without having to know a lot about the particular instances of each type of CRDT. So they have a nice programming abstraction. And then we've seen that while the programming abstraction is very nice, it can still be extremely expensive. And so we need to build mechanisms and invent protocols that allow us to do these things at low scale. So maintain a large cluster of nodes and efficiently disseminate state to those nodes. And so continuing in the future, we hope to grow this approach. We hope to continue to increase the expressiveness of the Lasp system. We'd like to explore new ways of enforcing invariants and what types of invariants we can enforce with weak synchronization, with the goal of simplifying distributed systems programming.
Welcome to the lecture on Just Right Consistency, the Antidote data store. My name is Annette Bieniusa. In this and in the following 2 videos, we will discuss the problems associated with consistency in geo-replicated data stores. We will see how consistency comes into play when we want to ensure invariance on data, and in the last part I will introduce you to Antidote, a transactional causally consistent data store. Let's start. Interactive distributed applications typically rely on shared mutable state to provide some sort of service. These applications support that data is shared between the same person using different devices, but also between different users of the system. You can share information in a social network like pictures and so on with friends or family members. Users want to be able to read and modify their data and interact with the application at any time. Therefore, it should be highly available, preferably even when being online. Further, data access should be fast. When an application takes too long to respond to a request, users will become irritated and eventually stop using this application. Therefore, low latency is business critical. Now, how do these systems typically are deployed and operated? The easiest way to deploy servers running distributed applications is to deploy them at data centers in the cloud. The data management is then typically handled by corresponding cloud databases. In a centralized deployment, the data is located in a data center at a single place. All clients connect to this data center and interact with the primary copy of the data. There's typically also secondary copies for data backup. However, this introduces non-uniform access latencies. Clients that are physically far away from the data center experience high latencies when they access the data. Further, if the data center is down, the data is not reachable anymore. Centralized deployments provide no fault tolerance in case of data center failures and might lead to temporary disruption of services. To prevent such situations, we want to replicate the servers and the data at different locations. In a geo-replicated deployment, we deploy several replicas of the database. So in this picture here, we have 3 database replicas, A, B, and C. Each client connects to the closest replica and interacts with it. The replicas themselves communicate with each other to synchronize updates, such that clients can access the data on any of the replicas. Geo-replication, as depicted here, leads to low latency when accessing data and also provides higher availability. When one replica becomes unreachable, clients can fail over to other data centers and interact with their data on the other replicas. Now, let's consider the situation when a data center is still operating but cannot connect temporarily with other replicas. When such a network partition occurs, there are actually 2 options. Option 1 is to keep the replica available. Clients can continue to operate against the local replica. The updates are then propagated asynchronously to the other data centers once the partition has been healed. However, the situation can lead to divergence of the replicas. Clients cannot observe the modifications by clients connected to another data center. Like if this client is modifying data item X, this modification is not observable by the client up here. So this client in this case reads older, stale, outdated data. Also, write conflicts can occur when 2 clients, say in data center B and C, modify the same data item. So if this client is also modifying data item X, we kind of have 2 different versions of X now, one that has been modified in data center B and the other that has been modified in data center C. Without using synchronization, it is not clear which version of a data item is the valid one. Also, when a client switches to a different replica, his updates may appear lost because they have not been propagated yet to the other replica. Application programmers have to consider these situations, which typically results in very complex application logic. The other option is to preserve consistency of the replicas. So instead of asynchronously propagating the updates, the replicas synchronize each operation before they acknowledge an update to the user. This helps to maintain a single system image. So updates that this client here is performing on data item X will only be acknowledged once they have been propagated both to the replicas A and C in this case. This approach is over-conservative if concurrent updates to replicated data only happens infrequently. So if we, for example, know that this client has very less likelihood to start reading data at a data center A and C, it will actually never see the difference in the system state. But the setup, so this choice for preserving consistency, simplifies the development of applications because programmers don't need to worry about divergent system state. The 2 options that we just discussed also manifest themselves in the CAP theorem. This theorem states that systems that have to handle network partitions have to make a choice between either being consistent under partition or available under partitioned. Data consistency models such as serializability or different forms of snapshot isolation are offered by CP systems. AP systems, on the other hand, trade the strong consistency guarantees given by the CP systems for higher availability. Typical representatives of corresponding consistency models are eventually consistency, so strong eventually consistency, and causal consistency. In the last decade, geo-replication actually became necessary for distributed applications due to the ever-growing number of users. Several popular cloud storage systems went for the promise of high availability and low latency. Systems like DynamoDB, Cassandra, or Riak offer geo-replication and scalability while being highly available, but they provide rather complex semantics. With these systems, programmers are faced with rather low-level programming interfaces, for example, key-value maps, where data items are associated to keys, and keys, for example, are collected in buckets. But there's typically no support for transactions, and there is no support for modeling relations in the data model. It turns out that this programming model, with its weak consistency guarantees, is rather difficult to apply as a programmer. More recently, cloud storage solutions start to emerge that bring back the strong data consistency guarantees and a more programmer-friendly interface at a high degree of availability. To prevent situations when the system is not available, this type of cloud storage relies on rather expensive infrastructure to minimize the likelihood of network partitions. So this gives us strong consistency. Typically, we also have support for things like transactions or SQL queries, but it still requires coordination across sites and incurs potentially higher latency. Typical representatives of these systems are the Google Cloud Platform with the Spanner database and also the Azure Cosmos DB. Let us summarize the important points from this video. The choice of a consistency model, as we have seen, has consequences for systems availability. CP systems typically provide strong consistency, but require expensive infrastructure to provide also high availability, and it also introduces higher latencies if we build our applications on top of CP systems. AP systems, on the other hand, opt for high availability, but provide weaker consistency guarantees and result in more complex data management. In the next part, we will continue our reflection of consistency models. We will discuss how data consistency comes into play when we want to preserve invariants on the stored data. In the second part of this lecture, we continue our discussion of consistency models. When choosing a consistency model, the programmer has to ensure that the model of her choice is actually powerful enough to ensure the correct handling of the data. So many applications have constraints that are defined on the data, but they may not hold when the operations execute concurrently under a weak consistency model. However, there may be other operations in the same application where the chosen consistency model is over-conservative and provides more guarantees than are actually needed. So it's very difficult to find a one-size-fits-all consistency model, even for a single application. The idea that we want to apply is that we actually want to tailor our consistency choices based on the application level invariance for each operation in the system at hand. In this part of the lecture, we will discuss different types of invariant. So we will start with AP-compatible invariants, which are invariants that can be implemented in AP system. These invariants require only one-way communication. This means that information can be propagated asynchronously within the system. In contrast, cap-sensitive invariants involve operations that require coordination and two-way communication. In the following, we will discuss these two types of invariants in more detail by looking at some examples. Let's start with AP-compatible invariants. These invariants allow to perform updates against the local replica and return immediately to the client without blocking. Information is then propagated asynchronously to the other replicas in the system, and this allows for fast updates and concurrent updates, and also availability even under network partition. As you have seen in previous lectures by Chris and Peter, Crdts, these conflict-free replicated data types, are actually the perfect data model for AP systems. They provide consistency even if in the case of concurrent writes. As we will see next, invariants that rely on relative order and joint updates can in theory also be preserved by AP systems. The application for which we take the examples in this lecture is FMK, the prescription management component of the Danish national healthcare system. The system provides functionality to create medication prescriptions for some patient involving doctors and pharmacies. It is further possible to update the medication of a prescription by increasing amount or adding new medication items. Further, prescriptions can be processed when a pharmacy delivers some medication that was part of the prescription. And finally, we have query operations that allow us to inspect the status and the content of a prescription. Now consider the following situation. Assume we have a geo-replicated system with two replicas, replica A here and replica B down here. Assume that a client connects to replica A and creates a prescription here that we will call P1 involving some medication A1 and patient. We will later update the same prescription by adding some new medication MAD2. These operations are then propagated to the other replica B. However, we actually need to make sure that a create prescription operation is delivered to the replica B prior to the update medication operation here. So we want to ensure that the ordering is respected at the other replicas. Why do we want to ensure that? Well, if we deliver the operations here out of order by first delivering the update medication operation and then the create prescription operation, we actually violate one of the program order invariants. Namely, we want to make sure that only prescriptions that exist can be updated regarding their medication. So this requires us to transmit the messages between the different data centers in the right order by keeping their relative order correctly. Consistency models that preserve invariants based on relative order are causally consistent. The idea of respecting causality when accessing data is based on the work by Leslie Lamport from the late 70s. Under causal consistency, updates are delivered in causal order to all other replicas. This ensures that no ordering anomalies can occur. So if an operation U happens before another operation V, and at some replica operation V is already visible, under causal consistency, we also require that operation U is visible at this respective replica. Causal consistency has been shown to be the strongest consistency model that is achievable in an AP system. Under this model, it is always possible to return some compatible version for a data object without communication with other data centers. As we've seen in the example, we can actually provide some form of referential integrity in AP systems which support causal consistency. This already makes causal consistency applicable in a lot of systems that are deployed in clouds nowadays. Now let us consider another example of an AP compatible invariant. Assume that we have again our two replicas A and replica B here of the data, and we assume that our client starts by creating a prescription on replica 1 and also propagates this operation here to the other replica. The client then updates the information on the doctor in prescription P1, updates the operation in the client, again forwards it to the other replica, and also updates the operation in the pharmacy. Now, in the situation that I'm showing here, we keep the updates causally consistent, so they applied in the same order on replica B as they happened on replica A. However, even if the operations are replicated in a causally consistent way, clients can observe an inconsistent object state. In a situation drawn here, the updates to the patient and the pharmacies have not been delivered at replica B, so they're kind of missing at replica B, when another client accesses here replica B and inspects the state of prescription P1. This leaves the prescription data in an inconsistent state, because partially the updates are missing. This situation can be avoided if the data store allows to group updates into atomic operations. We call these also atomic updates sometimes in transactions. All updates corresponding to such a transaction are delivered together and made visible together at every replica. Further, transaction can be used to expose the system state to clients in form of causally consistent snapshots. This isolates concurrent transactions from each other, so we don't see transactions being only applied in parts. And this also supports further kinds of data invariants when we have this all or nothing properties on snapshots. Transactions are then also can also be delivered in causal order, just as we have seen this for these single operations. Adding transactional reads and updates to the causal consistency model, we obtain a consistency model called transactional causal consistency. Under this model, operations are delivered in causal order. Further, client reads are based on consistent snapshots, so clients only observe consistent snapshots, and writes happen transactionally in an all or nothing fashion. This plus here indicates that we here assume that concurrent updates converge to the same value for all replicas. So this is, for example, given when we operate on Crdt data models. We kind of get this convergence for free. So now we've seen two examples of AP-compatible systems, however, or AP-compatible invariants. However, not all invariants are AP-compatible. Consider the following situation. Let's assume our system actually consists now of 3 replicas, A, B, and C. The invariant that the system needs to maintain is that medication is delivered at most the number of times that it is actually contained in a prescription. So in the situation here, we assume that we have a prescription for 2 doses of some medication. And we don't want to over-deliver medication. Now, assume that we start processing the prescription on replica A. So on replica A, we have a client asking for 1 dose of the medicine, and such, this process prescription operation is reducing the amount of this medication by 1. Before executing the update, replica A needs to check the precondition. Is there enough medication left over in the prescription? It kind of holds, so we require 1 item of medication and there's 2 available. So on replica A, we kind of perform the update and forward it to the other replicas. This results finally in all replicas having 1 prescription for this medication left over. And you see, it's again a consistent state. All these replicas see that exactly 1 medication item is left over. Now consider a scenario where the prescriptions get processed on different replicas. So in the example here, we again have replica A, where in transaction T1, one item of the medication is supposed to be retracted from the prescription. On replica C here, we have another transaction that processes the prescription by adding 3 items to it. Both replicas check before applying their operation whether the precondition is fulfilled. So in this case, the replica has a state that 2 medication items are left over, so it's safe to subtract 1 from them. In the case when we add more medication items, we actually don't even need to check the precondition. Assuming that it holds prior to the operation, it will also hold after the operation. So after both transactions have been applied locally and propagated to the other replicas, all replicas again converge to the same state, namely to a state where the medication item is available for 4 more times. So the precondition that enough medication is left over in order to apply an operation is stable under concurrent addition. So whenever we add more items, this operation is kind of safe. However, consider now another scenario. So again, on replica A, we reduce the amount of medicine by 1, but now on replica C, we want to reduce the amount of medicine by 2 more. Both these replicas locally check their precondition. So it is safe on replica 2, assumingly, to reduce the amount of medicine by 2. It's also safe to reduce the amount of medicine by 1 if we only check locally here on replica A. However, if both these transactions are executed and propagate to the other data centers, this results in a system state where we suddenly violate our invariant, that the number of medication items delivered should always be within the range that a prescription allows. So it turns out that our precondition, checking whether there's enough prescriptions available, is not stable if we concurrently reduce the number of prescription items. The discussion on these 2 types of invariants concludes the second part of this lecture. By using the examples from the FMK application, we have actually seen that strong consistency is often too conservative. There were cases where we could safely execute operations without requiring cross-site two-way communication. Causal consistency, as we have seen, ensures that relative order invariants are preserved, while transactions add further guarantees regarding the atomicity of operations and isolation for grouped accesses to data. In some situations, however, coordination becomes unavoidable, as we have seen in the last case with the medication items. For these so-called cap-insensitive invariants, sporadic synchronization can be used to provide stronger guarantees without enforcing too much consistency in the general case. In this last part of the lecture, I will introduce you to the Antidote data store. This is actually one of the research results of our projects SyncFree and Meiklejohn. Antidote is an AP data store for geo-replication in the cloud. This data store implements the CURE protocol, which provides transactional causal consistency. This is the consistency model that we discussed in the last part of the lecture. Recall that transactional causal consistency is actually the strongest consistency model which can be implemented by AP systems. Antidote further offers a comprehensive interface for programmers. It provides abstract data types in form of conflict-free replicated data types, CRDTs, including maps, sets, sequences, and different types of counters. Therefore, programmers do not need to worry about potentially conflicting writes. Concurrent updates are merged automatically dependent on the respective data type semantics. Antidote further offers a transactional interface. So all reads within a transaction operate on a causally consistent snapshot, and all reads are isolated from currently running transactions this way. Updates are applied in an atomic all or nothing fashion, and in contrast to other AP systems that do only provide eventual consistency as their base consistency model, applications in Antidote can use non-normalized data layout because Antidote provides means to guarantee referential integrity, as we've discussed in last lecture. For certain types of cap-sensitive invariants, Antidote also has built-in support. For example, it provides a counter data type that maintains the invariant that the value of this counter never goes below some predefined bound. We call these counters bounded counters. This data type allows programmers to insert coordination only at few well-defined places. This way, she can choose just the right level of consistency that is necessary for the application at hand. Let's have a closer look at how Antidote looks like from the inside. So here's a sketch of its architecture. Antidote nodes consist of several core components. We have a transaction manager that deals with snapshots and atomic updates. The materializer is an in-memory component that provides fast access to recently written versions of a data. The log is responsible for storing data persistently on disk, such that in case of faults, we can reconstruct the state from this disk version. And the intra-DC replication deals with synchronization between the different data replicas located at different data centers. These components together form a node in Antidote. We typically deploy several nodes within one data center and shard our data across these nodes in order to provide better load balancing. These nodes are forming together a cluster, so every data center kind of maintains a cluster, and these clusters between data centers then communicate their updates following the CURE protocol. Clients connect to the data center that is closest to them. For clients to connect, we actually offer different client bindings for different programming languages. Here in the slides, we see a code snippet from an application using the JavaScript client library. In order to connect with the data store, we first need to establish a connection. So in the example here, we assume that Antidote is available at localhost under port 8087, and we use the connect function here to obtain access to a connection object. Next, we choose a bucket in which we want to place a new object. So we use here as default bucket a bucket called bucket1. The instruction set here generates a new CRDT or set in the bucket under the key programming languages. With the operations add all, add or remove, we can modify the entries in the set. So add all adds two strings, namely Java and Erlang, to the set, and then updates the corresponding data item. Finally, we can obtain the current set entries by reading the content of the set. These mentionings of await here ensure that the program waits until the update and read operation have been completed before executing the next step, thus synchronizing the different data accesses. We can also operate on the data using transactions. So here's an example for usage of the transaction APIs. Antidote offers two types of transactions. Dynamic transactions allow to compose reads and writes to data items at runtime dynamically. So we have here, for example, the updates to some set by removing a data item, setting a data item, and we could determine now really at runtime, for example, based on the actual content of the set, what the next operations in this transaction should be. For static transactions, when we already know when writing the program statically at compile time, which operations will be applied on which objects, we can also just group the updates into batches that are applied atomically. So this update here is actually, this batch update here is actually also a so-called static transaction. This concludes the third and last part of this lecture. Antidote is a data store providing just right consistency for geo-replicated systems in the cloud. The consistency model can be adapted to be just right for the respective application. This way, AP-compatible invariants can be maintained with the support of transactional causal consistency. Similar joint updates can be done, and we even have support for cap-sensitive invariants that can be implemented using bounded counters. Antidote offers for programmers a rich interface, including transactions with snapshot reads and atomic updates, and also Crdts as data model that avoid conflicting updates, so the programmer does not need to deal with them. If you want to learn more about Antidote, you should consult the documentation of our webpage under antidotedb.org. The code is also freely available at GitHub, and you're very welcome to join our developer community. Thank you.
We have now arrived at the end of this lesson on how to program a distributed system with weak synchronization. We've shown that with a weak synchronization model, namely eventual node-to-node communication, we can provide a pretty strong consistency model, namely strong eventual consistency. And we've applied this idea in three areas: Crdt, which is the basic data structure, Lasp, composing Crdts, and Antidote, transactional database based on Crdts. But now, in this video, let me talk about the future. And in our view, there are two main areas in which this approach will have a big effect: edge computing and synchronization-free services. But in order to present these right, let me first talk about consistency models. So the first model that people traditionally talk about is called strong consistency, where the system is linearizable, which is considered easy to program but can be very inefficient if the nodes have large latencies. This leads to eventual consistency, where the system can support many concurrent operations in flight. So you can start many operations concurrently, and they will be being executed at the same time at different parts of the system. So this is much more efficient in execution, but these operations may conflict with each other, so it can be hard to program. And this leads to the third approach, which I call convergent consistency, where the system again can support many concurrent operations, but in addition, it obeys strong eventual consistency. And the idea is that it's efficient, but also easy to program. We cannot do cap, but we can do AP plus convergent C, available, partition tolerant, and convergence. So let me talk now about edge computing. It turns out, in today's internet, distributed systems at the edge are omnipresent. Internet of Things and mobile devices far outnumber data center nodes, and the gap is growing with time. There's no way that the data centers can handle all these devices. And the networks on the edge are highly dynamic. The computation is highly dynamic, nodes coming and going, communication, the network is very flaky. It turns out synchronization-free programming is well matched to this kind of system. Combining convergent computation with hybrid gossip communication layer, it's naturally tolerant to the faults that occur in edge systems. So the green here are faults related to the network, so partitions and message loss reordering. The only effect that they can have is to slow down convergence. No other incorrect operation is possible. And the second kind of problem here in blue, which is node problems going offline, online, for low power nodes, node crashing, the system will tolerate this as long as some nodes have the state. So it turns out that the models we've been talking about in this lesson are well adapted to edge systems. And now let's talk about the second promising direction, which is synchronization-free services. So in today's systems, we use Crdts as the basis for a programming framework and transactional database. Basically, it seems we're using it for a particular kind of way of doing things. But it turns out in the future that this approach is actually much more general than one might think. So let me explain this by giving you a little story, a little parable, which I call the parable of the car. So here's a car driving on a highway, and the car is a mechanical construction that uses friction. Now, friction, like synchronization, is sometimes desirable and sometimes undesirable. For example, the tires grip the road, and the only reason they grip is because of friction. So the car needs friction to grip the road. But the motor, internal to the car, avoids friction. The motor should be as frictionless as possible. Otherwise, it will heat up and wear out. So you can see that friction is desirable at the external interface, but undesirable inside the system. Now, applying this to distributed systems, consider here in the blue box a distributed computing system spread over many nodes. It consists of services that are talking to each other. And me, as a human user, I am talking to this system. So as a human user at the external world, I will synchronize with the system. Synchronization is only needed at the system's interface with the external world, like friction, which is only needed externally. But internally, the services should avoid synchronization. Between them, the services should not use synchronization. Basically, the system has a synchronization boundary. Inside this boundary, all services are synchronization free, and the synchronization is only needed at the boundary. Services in this system should be inside the boundary, and in that case, they should all obey strong eventual consistency, and their API should be asynchronous streams going in and out. And if you do that, then internally the services will be using this weak synchronization-free model. Okay, so how do we go forward now? So in this lesson, we have shown you the basic concepts of programming with weak synchronization, CDT, Lasp, Antidote, and I've explained the future work, edge computing and synchronization-free services. In fact, myself and my partners are part of the LightCone Horizon 2020 project in the European Union, which is working, starting as beginning points, both Lasp and Antidote, but going much farther. And for those who are interested, we provide documentation and code if you want to try out Lasp and Antidote, and we also present a bibliography for further reading.